To measure how sound behaves inside a room, modern acoustic engineering relies on precise rules, anchored by the ISO 3382-1 architectural standard. This standard assumes a diffuse field. Sound must reverberate evenly, so acoustic measurements remain the same anywhere in the room. For this to exist, an environment must be large and uniform, producing a sufficient density of acoustic modes, like contemporary concert halls. To test these spaces, engineers place microphones at various points and emit frequency sweeps using an omnidirectional source, like a dodecahedron speaker. They record data from multiple positions, averaging them into a single representative metric for the room. These tests prioritize the mid-band frequencies, typically averaging the data exclusively between 500 and 1000 Hz. This happens to be the frequency range most likely to cause hearing damage in a modern workplace. By averaging out spatial variations and ignoring extreme high and low frequencies, acousticians can efficiently evaluate and tune uniform architectural spaces for contemporary use. Applying this strict industrial standard to the irregular spaces of antiquity creates a severe methodological blind spot. The mathematical averaging required by the ISO standard completely erases the most important acoustic phenomena present in archaeological sites. To understand how human acoustic ecology evolved over 40,000 years, we must abandon standardized averages and examine the localized extremes. The first case study in this evolutionary timeline sits deep underground in the Palaeolithic cave systems of northern Spain. If an acoustician applies standard mid-band averaging, calculating the decay of sound between 125 and 2000 Hz, these caves present a mathematical illusion. This chart compares the averaged early decay time of the La Pasiega and Tito Bustillo caves to modern venues like the Royal Festival Hall. The data shows a variance of only 1 to 4%. On paper, these ancient caves look acoustically identical to a modern performance hall. That statistical similarity is entirely false. It is the direct result of ignoring frequency extremes and flattening the data into a clean average. This is a line graph mapping early decay time across specific frequency octaves. When we shift our analysis down to the 63 Hz octave, massive, isolated data spikes appear for the Las Chimeneas and El Castillo caves. These are severe modal resonances. They exist powerfully at 63 Hz, but drop off exponentially as you move into the higher frequencies favored by standard testing. Engineers strictly following modern protocols miss these low-frequency modes twice. First, through mathematical averaging, and second, because standard dodecahedron speakers often fail to emit significant energy below 100 Hz. Researchers ran logistic regression analysis on the spatial layout of these cave systems, mapping the exact locations of these low-frequency anomalies against the archaeological evidence. They found a direct correlation. 40,000-year-old painted motifs, like these reddish-brown bison, are placed exactly where these low-frequency resonance modes are most intense. Early humans were actively navigating these cave systems, identifying naturally occurring acoustic extremes, and visually marking those specific nodes. By the year 2500 BC, massive Neolithic monumentality provides the next evolutionary step. Instead of searching for naturally occurring resonances underground, humans began using heavy architecture to intentionally generate acoustic anomalies on the surface. Digital acoustic modeling using ray tracing software on the Phase C layout at Stonehenge reveals severe spatial disparity across the site. This frequency response graph contrasts two receiver positions. The outer edge of the Sarsen circle presents an extremely dry early decay time of 0.38 seconds. The exact center of the monument is highly reverberant, jumping to over 1.5 seconds. Averaging these two positions together, as dictated by modern standards, would output a moderate decay time. That average environment exists nowhere in the actual physical space. This extreme disparity is caused by the physical geometry of the stones. The circular arrangement forces complex, overlapping patterns of sound focusing. Elliptic focusing traps and directs sound between the inner stone arrangements. Parabolic focusing radiates outward, reflecting off the largest central trilithons to project audio across the site. Hyperbolic focusing redirects that sound even further, pushing it toward the outer periphery of the circle. Because of this intense concentration of reflections, a person speaking from the exact center of the monument suffers a massive drop in speech clarity, measured as C50. The immense local reverberation muddies their own voice in their ears. Because of the circle's geometry, the speaker struggles to hear their own words, while simultaneously acting as a highly direct, amplified sound source for everyone standing on the outer edge. These generated acoustic disparities were highly localized. The specific anomalies dictated the physical utility of the monument and the ritual hierarchy of anyone standing inside. By 300 BC, the Hellenistic Roman theater at Paphos marks the transition to engineered uniformity. Unlike the chaotic low-frequency nodes of the Palaeolithic caves or the extreme spatial disparities of Stonehenge, Paphos exhibits conscious, deliberate engineering designed to achieve uniformity. This line graph plots the early decay time across the 125 to 2000 Hz spectrum. The response lines are tightly clustered and incredibly flat across the entire range. This flat response aligns seamlessly with modern engineering capabilities. Acoustically, this 2,000-year-old open-air theater functions almost identically to a modern Philharmonic hall. This is the specific point in history where standard acoustic metrics and assumptions finally align with the actual architectural intent of the space. To fully evaluate this engineered environment, we can use two distinct modern metrics: articulation loss of consonants and C50 speech clarity. These metrics reveal a highly stratified acoustic quality deliberately across the audience seating. Row 3 possesses mathematically ideal speech clarity. As you move further back, that clarity degrades in a predictable, linear fashion, reaching poor intelligibility by row 14. Acoustic ecology is no longer emergent. By the Hellenistic era, sound has been mathematically harnessed by architects to enforce strict social and political stratigraphy. The physical record maps a distinct 40,000-year transition in human acoustic ecology. Phase 1 is defined by the animistic appreciation of natural, extreme low-frequency resonances deep underground. Phase 2 shows emergent spatial focusing actively generated by the geometries of megalithic monuments. And Phase 3 achieves the secular, engineered control of Roman performance spaces. But this evolutionary history cannot be understood using the rigid industrial assumptions built into modern standard acoustic engineering. We have to re-evaluate the very concept of a data anomaly. Extreme low-frequency responses, severe spatial variance, and concentrated nodal behaviors must not be averaged away as artifacts or testing errors. To accurately map human history, our methodological tools must be decoupled from modern standards. In the study of antiquity, the acoustic anomalies themselves were the exact phenomena that defined the architecture.